In today's lecture, we will study about the equipment that could be used for the power factor improvement. Power factor calculations will be made, and after that, importance of power factor will be studied based on the equipment and also on the cost of equipment. Now, generally we see that the acceptable power factor of the load lies between 0.8 to 0.9, and as discussed in the previous slides as well, if the power factor drops for any particular reason, we can improve it by using one of these equipments, which could be a static capacitor, asynchronous condenser, or a phase advancer. Alright, so if we start from the first one, the first equipment here is a static capacitor, and as discussed earlier, a capacitor is generally connected in parallel with an already connected lagging load. So if I draw a circuit of a single phase circuit, so let's say that's the source, and let's just assume that we have a RL load. And what we do, we just connect the capacitor in parallel. Okay. And this capacitor, in this case, will draw leading current and will try to neutralize the already lagging current. We saw that already in the previous lecture. And in the previous lecture, we also computed an expression for total reactive power after the power factor correction. And if I just write it down, the expression was VI dash, which was the compensated current, sine of phi 2, which was the corrected angle after the equipment being used, and that is equal to VI sine of phi 1 minus VIC. And if I take this VIC on the left hand side, this I can rewrite again, VIC equals to VI sine of phi 1 minus VI dash sine of phi 2. Alright, and let's say if I assume that this is the reactive power being drawn by the capacitor, then that could be written as QC equals to and also if I, for the sake of conversion, if I just add, multiply cosine of phi of the same angle and divided by the same thing, which is a cosine phi, which is a power factor on this side, and again if I do repeat the same thing by multiplying by cosine of cosine phi 2 and divided by cosine of phi 2, then these two portions, these represent the active power component before and after the compensation. So QC can be written as P1 tan of phi 1 minus P2 tan of phi 2. Okay, so we have derived this expression, and we'll be using it in the upcoming slides. Alright, so at this point we can see that the power, the lag between the voltage and the current can be compensated. But if we want to know what is going to be the capacitance, the value of the capacitance which we are going to be connecting, so let's say if you want to calculate the capacitance over here, and we also know the expression which is QC equal to VIC, then this can also be written as V times V divided by the reactance, okay, and that can be equal to V square divided by 1 over omega c, and eventually this will be equal to V square omega c, and from here we can compute the value of the capacitance. That will be equal to the reactive power drawn by the capacitor divided by the angular frequency times the voltage coming from the supply. Okay, so this is calculated for a single phase circuit. Now if we look at the figures here, we can see there are two figures, and both of these figures have a three-phase load, and we don't know the configuration of the load in which it is connected. It could be delta, it could be Y, but right now it's looking like it's a delta connected load. But anyway, what I'm trying to say is that in these cases we have two configurations, and the set of capacitors here, they can be connected either in delta configuration or in Y configuration, irrespective of the load configuration in whichever they are connected. So let's say if we want to calculate the value of the capacitor which are connected for a three-phase load, in that case we know that for a three-phase connection, this connection here, we can see the capacitors are connected in delta. So for a delta connection, we know that the phase voltage coming in will be equal to the line voltage. We know that, and in that case the capacitance of the delta connected capacitor will be equal to the reactive power being drawn and divided by the omega Vp square, or it could be equal to Qc divided by omega VL square. Okay, makes sense. Now if we want to see the capacitance for a Y connected capacitor set, then we also know that the Vp phase voltage for a Y connected circuit is going to be equal to V load divided by √3. Okay, so in that case the Cy will be equal to Qc over omega Vp square, and that will be equal to Qc divided by omega line voltage divided by √3 square, and this is going to be equal to 3Qc divided by omega VL square. So from these two expressions we can see that the capacitance in Y connected the capacitors being connected in Y configuration, the value is 3 times bigger than the value being connected in delta configuration. So if this is the case, let me write it down. So let's say if this is the case, C delta equal to 1 by 3 of Cy, then and at this point if we want to know that which configuration will be preferred in whichever case, so we have concluded on this point, but now if we want to know which one is preferred, then in that case, and we also know that that the voltage rating of the delta equal to V delta equal to √3 of Vy, then that means for higher voltages, like for higher voltage applications, we are going to prefer delta connection over the Y connection, because the delta connection is is rated for higher voltage than the circuits in Y configuration. So with that, this is a small little analysis which I've done. It is not in the book, so it is just for the sake of understanding and understanding on what we have to prefer at certain case when we have two configurations given. So now if we want to talk about the advantages of static capacitor, we can see that they are practically loss free, and once they are installed, we don't really have to worry about them for 5 to 8 years. That means they require very less maintenance, and they are also robust and do not require much space, and also they don't require any special equipment for installation. Furthermore, they are not much sensitive to temperature, other atmospheric condition as well. So these are the advantages, and after discussing the advantages, there are definitely some limitations as well associated with it. So the first disadvantage is that the smooth control of reactive power is not possible, especially when the system needs to be connected or disconnected. However, this can be controlled with the help of synchronous condenser, which we'll study in the next slide. The second disadvantage is that they cannot withstand overvoltage above 10%. So, and the last disadvantage is that they are hard to repair, and once they are damaged, they are usually replaced. Now, the second equipment that is generally used in industry is a synchronous condenser, and synchronous condenser is actually a synchronous motor, and by varying the field current, it can be operated as a leading or a lagging load. The reason for using a synchronous condenser is that in industry, usually synchronous motors are already existing, and instead of installing capacitors, which could be expensive, these motors which are already available can do the job. Now let me give you an example. For instance, we have a system connected. On the left hand side you can see the figure. There's a three-phase load connected with a three-phase synchronous motor. If you remember, in the case of static capacitor, we calculated the capacitance to be connected, but in this case we will be adjusting the power factor by varying the field current. So if this motor which is connected draws, let's say, 50 kilowatt, and the reactive power which is desired to be supplied to the motor is, let's say, Q is 10 kVR. So let's say if we want to calculate the power factor, first of all we will calculate the apparent power, which is P square plus Q square. Let's say this is equal to X, and we know the power factor will be equal to cos inverse of active power over apparent power. So let's say that is equal to Y. So to achieve the power factor, which is Y, the current will be altered. And how do we do it? That we'll learn in the machines course, how the way we change the field current. So if we look at the figure on the right side, IL is the load current drawn, whereas IM is the leading current drawn by the synchronous condenser, and I is the phasor sum of IL and IM, and this is the corrected current or the compensated current. Now if we talk about the advantages of synchronous condenser, The synchronous condenser offers smooth transition from one stage to another because of slow dynamic response of the machine. Also, the amount of current drawn can be controlled by the field excitation, and the synchronous condenser can also operate at overload condition for short duration, contrary to the static capacitor, and its windings can withstand higher temperature differences. Now, talking about the disadvantages, since the synchronous motor contains winding and rotating parts, there are losses associated, and also the maintenance cost is high, and its efficiency is lower due to iron losses, and there's also a noise factor. It is also expensive than static capacitors for power rating less than 500 kilowatt ampere. And the next is that the synchronous motor are not self-starting, so some auxiliary equipment will be needed for that, and that will definitely increase the cost. So these were the two equipments which are usually used for improving the power factor. We are not covering the third case, which was the phase advancer. Now, moving on, we have learned that power factor can be improved by adding a capacitor in parallel, and leading IC, the capacitor current, will neutralize the lagging current and drag the resultant current to a smaller degree. Now, the figure shown here represents the current phasor before and after the correction. So this is, let me change the color. Let's say this is red. Okay. So this is the current phasor before the compensation, and this is after the power factor correction. Here, the side AB, on the right hand side, the side AB is segregated into two parts, where the reactive power being drawn by the load can be seen as AB, okay, which is the reactive part or the reactive power with respect to phi 1. So this portion, this complete from air till air, this is going to be the reactive power drawn by the load, and the corrected or the reduced reactive power is AC. So this portion here, this reactive power is the reduced reactive power when the power factor is improved, and the KVR is reduced because of that power factor correction, and this portion BC is actually the reactive power supplied by the correction equipment. So this KVAR1 was the initial reactive power being drawn, and this was KVAR2 is the reactive power after the power factor has been corrected. So there is a obvious reduction. So at this point, if we want to calculate how much of leading reactive power was supplied by the capacitor, that is going to be equal to BC, which I already explained, and BC will be equal to AB minus AC, and that is reactive power 2 subtracted from reactive power 1. And again, as discussed in the case of static power capacitor, which was being connected in a single phase, we will derive the same expression again, but with the help of the power triangle, which is given here. So the expression which we derived earlier was QC equal to P1 tan of phi 1 minus P2 tan of phi 2. And we also know that when the power factor is corrected using, let's say, a static capacitor, then it doesn't make any difference to the active power being drawn. So P1 and P2 can be taken as a common P times the tan of phi 1 minus tan of phi 2. So this was derived using the static capacitor. But now in this case, we are going to derive the same expression using the power triangle. So what we do is we just apply a simple Pythagoras theorem where the reactive power is equal to the active power times the tan of the phase difference. So this OA is the P and times the tan phi 1 minus tan phi 2, and that can be represented in the form of kilowatt. So this is how we can also derive the same expression for the reactive power or the leading reactive power. It was actually drawn by the capacitor, so that is why it is called leading reactive power. Now, okay, so after discussing the power factor correction methods, we will now proceed towards the its economical advantages or importance. From consumer, there are two point of views: consumer and generating station point of view. So from consumer point of view, usually the domestic consumers operate close to unity power factor. But however, when it comes to industrial consumers, if the power factor is improved, the maximum demand in kVA will reduce. We have seen that already. We can all elaborate it with the help of this expression. We know that the maximum demand in kVA or kVA equals to kilowatt active power divided by the power factor cos of phi, or this can be called peak active power. Okay, so even though with the power factor correction, initial cost of the equipment will increase anyway, but it reduces the overall kVA demand, which results in net annual saving. Okay, and from a generating point of view, generators, you know that they are usually designed without any loading information, but the useful output, which is in kilowatt, depends on the real power being demanded from it. So from this expression here, number of useful units, they depend on cos of phi. Therefore, the greater the power factor of the generating unit, higher kilowatt it can deliver to the system. And an improved power factor also leads to improving earning capacity of the power station. Okay, so now the next topic is to find out the most economical power factor. From the previous slides, we have come to know that by introducing power factor correction equipment, the kVA demand decreases to some new value. So let me draw the triangle one more time. So let's say if this was the case initially, where this was the angle phi 1 and this was the current phasor voltage, and if we represent it in the term of power triangle, then this was the apparent power, this was the active, and this was the reactive power. So when this was improved to some new value, let's say phi 2, then this became S2 and this portion became Q2, and Q1 was from here till this point. Okay, so the kVA demand decreases to some new value, which is S2. So with the reduction in kVA demand, the charges on the consumer also reduces. We can take an example of any generic tariff considering the kVA and the kilowatt parameters, such that Let's assume that this was the total charges of the tariff, which was equal to, let's say, two-part tariff, that was equal to kVA demand plus kilowatt demand. So this portion here, this as the kVA parameter. So if the kVA demand reduces, the overall tariff or the bill is also going to get reduced. But in order to bring down the, let me change the color. If we want to bring down the apparent power from S1 to S2, obviously there's some extra equipment required, which will increase the initial investment as well as the form, and like it will initially increase the investment in the form of annual interest, and it will also increase the depreciation charges as well. So therefore the net saving, the actual net saving, can be equal to the savings in maximum demand charges minus the annual cost of the power factor correction equipment. So this is going to be the expression for the net annual saving. And with that, we can come up with the definition that the value to which power factor should be improved so as to have a maximum net annual saving is known as the most economical power factor. Okay, so far the definition has been cleared up. Now to calculate the most economical power factor for a system, it usually consists of two parts. Let us assume that a consumer is taking a peak load of peak kilowatt at a power factor of angle phi 1 or power factor cos phi 1, and is charged at a rate of rupees X per kVA of maximum demand per annum. The second part is that after the power factor correction, where the power factor becomes cos phi 2, the rate charged for the power factor improvement equipment will be rupees Y per reactive power or per kVAR per annum. So these are going to be two parts which are going to be combined together to work out the most economical power factor. So first of all, we will try to calculate the annual savings in the form of reduction in kVA charges or in reduction in the maximum demand charges. This one. Okay, before we go ahead, let me draw the diagram one more time. So it will be somewhat like this. Okay. And another current phasor. Change in color. Okay, so let's say this is O, A and B. Phi 2 and phi 1. This is kVA 1. This is kVA 2. This is kVAR 1. And this is going to be kVAR 2. Okay, and this will remain as kilowatt. Alright, so with respect to the triangle, it will be equal to rupees X times the change in the kVA or change in the apparent power, where kVA is equal to kilowatt divided by the cos of phi, which we learned from the power factor formula. So overall, it can be represented in the form of secant, like active component times the secant of the both angles before and after the correction. Okay, now calculating the annual cost of power factor correction equipment which is rupees Y times the difference in reactive power drawn before and after the power factor correction, where kVAR equals to kVA sine of phi. This, and if we take if we convert it into kilowatt, then this is going to be sine over cos phi, and kVAR equals to kilowatt times the tan of phi. So as I just said, the change in reactive power is going to be which it was kVAR2 and it was changed into kVAR1. So the annual cost of the correction equipment will be this, and the total net annual saving will be the expenditure in equation 1 minus the expenditure in equation 2. So that was the maximum demand charges minus the cost, and that is going to be the net annual saving. So it is the saving, not the total expenditure. So we must keep this thing in mind. So this is net annual saving. All right. Now there's another thing which we need to highlight here, that the values x and p, which is active power, and the angle phi 1 and the y, they are all constant except for the variable quantity, which is phi 2, because this will be varying depending on the reactive power being demanded. So phi 2 is the variable, and to achieve maximum annual saving, the rate of change of phi 2 with respect to the saving should be 0. So that means ds by d phi 2 should be equal to 0. And if we plug in the values of s from the previous slide, it will be equal to this, and the differential expression can be segregated in the form of angle phi 1 and phi 2. So we segregate both of these angles, and the constant terms will be equal to 0, and the phi 2 can then be computed all the way down to phi, sine phi 2, and that is going to be equal to y by x. And now if we convert this into cos of phi in terms of power factor, then it will be equal to this final expression. And from here we can conclude that the most economical power factor depends, the economical power factor, which is cosine of phi 2, depends only on the relative cost of supply and power factor correction equipment, and it is independent of the initial power factor, which was phi 1. So there is no component of phi 1 included in this final expression of the most economical power factor. Okay, so after understanding the economic value of the improved power factor, we will now try to learn what to do if the power station is required to deliver more power to meet the demand of increased load. So in this case, there are two ways which can be adopted. We can either increase the kVA generating capacity of the power plant at the same power factor, or by improving the power factor of the system such that the required kilowatt or the required active power can be supplied by the same power station. So if I represent the whole idea in the form of a figure, it will look like this. And what we can do is the first method is to increase the kVA capacity. So if the kVA capacity will be increased, then this extra demand can be satisfied. So let's say this was P1, and let's say if extra demand is P2, then the first thing which we can do is to increase this kVA supply. Okay, and the next part is that when we increase this kVA supply, the power factor will remain constant. But the second method is that we can improve the power factor. So in that case, it will intersect this increased load diagram at this point. Okay, let's say at this point. So this portion is going to be the extension or extended part when the cos phi is reduced to phi 2. So there are two ways to meet this load. I'm going to explain it in a better way in the next slide. So again, in this slide, to achieve extended load, what we can do is increase the kVA capacity. That was the first method. And the second method, what we can do is, for this increased power demand, which is this, we have improved the power factor. So the power factor has been improved, and by this way we can satisfy this demand load. Okay, now keeping this in mind, in both of the methods described above, extra capital investment will be required. And to perform a detailed analysis, let us compare the cost involved in both of the two methods. Now let us consider the initial load on the station is P1. Okay, and supplied at power factor cos phi 1, and with the kVA rating of the plant is S. So OB equals to S, apparent power. So if the demand is increased to P2, so let's say P1 was OA and P2 is OC, then kVA supply of the plant should increase to OD. So it was OB initially, and it has increased all the way to OD. Okay, this we understand. Which means that BD is the extra capacity which should be increased. So BD, this portion in red, is the extra capacity which should be increased, but for the same power factor, which was phi 1. So that was the first case, or the first method. In the second method, it is that the same power P2 can be supplied by improving the power factor from cosine 1 to cosine 2. That is, the apparent power OB will remain equal to OE, and that is also equal to S. Now, after understanding the comparison between the two methods, let us work out the cost involved in each of them. So the first one is the cost of increasing kVA capacity, that is BD. So if capacity is increased at the same power factor, then this angle is going to remain phi 1. So BD, which is the hypotenuse, so this is going to be phi 1. So BD, which is the hypotenuse here, can be calculated as BF divided by cosine of phi 1, or it can be equal to AC divided by cosine of phi 1. Now this AC is equal to OC minus OA, which are also the x components of the triangle OEC and OBA. So OC and OA are the x components. So that means it can be represented in the form of cosine. So after that, the final expression will be equal to this. And since OB is considered equal to OE, the apparent power will be equal to S in both cases. So, and if rupees X is the annual cost per kilowatt of the station, then the annual cost due to increase in kVA capacity will be equal to equation 1. Now, for the second case where power factor is improved to meet the load demand by maintaining the same kVA rating, as the curve OB was shifted to OE, and the leading reactive power taken by the capacitor will be ED, this, which is equal to CD minus CE. Alright, where CD equals to OD sine phi 1 here, OD sine phi 1, and CE equals to OE sine of phi 2. Now OD is also equal to OC divided by cosine of phi 1, and to convert it equal to OE, OC is further equal to OE cosine of phi 2. So the final expression is S times tan of phi 1 cosine of phi 2 minus sine of phi 2. So with that, if the rupees Y is the annual cost per kVAR reactive power of the power factor correction equipment, then the annual cost will be equal to equation number 2. Okay, so both of the costs are calculated. So from the previous slides, equation 2 represents cost of power factor correction equipment, and equation 1 indicates the extra cost required for expanding the kVA capacity. So the power factor correction equipment, which is number 2, is cheaper when the expenditure here are lesser than the expenditure in 1. So by plugging in the values, and we will have these two expressions, and where apparent power can be cancelled out, and then it will be this, and then afterwards the tan is represented in the form of sine and cosine, and the eventual goal is to segregate the sine and cosine values on the both sides, and then in the end, from the final expression here, we can tell that the value of y should be less than x times the cosine of phi 2 minus cosine 1 and all of this, to be able to become the economical method or the more economical method. And the limiting value will occur when both the left and the right hand sides will be equal, which means it won't make any difference if we choose extension of plant capacity or we choose power factor correction equipment. Both of them will give the same expenditures, and that is called the limiting factor. So with that, I will conclude my today's lecture, and see you next time. Thank you.